d gamma 2 by dt at t, this was 0. So this, of course, when you solve for it, I put both of them as constants, which is of course rubbish. So so gamma 1 of t is some t plus k1. Gamma 2 of t is k2. Now we use the initial condition. So these k1, k2 constants. And so now we use the initial conditions. So so the initial conditions, what was it? So gamma 1 0 to be p1. So the first gamma 2 of 0 to be p2. So p was our chosen point, right? So this of course changes the nothing in some at some level. So this means k1 is still p1, and k2 is p2. So but of course the integral curves, so the maximal integral curve is so t plus p1 and p2. So that was one remark. So the other one was so perhaps answering the why here. Maybe some of you saw this already, but because so in the first equality, what we had used was just the definition. Yeah. So from going from the first equality to the second equality, we use the fact that gamma was integral to y, the vector field y on W. So that actually reminds me, I had written also that I think I had written here as S. So we define a vector field y on S. That should be W, of course. I remember writing it as S yesterday. So of course it has to be W. Maybe I changed, I don't remember. But okay. So because on S itself, you then see that y and x1 coincide and so on. So, okay, so why are these two orthogonal? Why is the gradient orthogonal to y? So that is merely by the definition of y, because you see definition of y was, so either you can see it by calculating it out, or you can see it by actually noticing that it is uh, uh, the component along x1. Yeah, so it's just a little calculation which I will do for you. Perhaps many of you see this or did this already. Nonetheless, so you just use the definition of y here. So let me write it on the next line. So because it will be a long expression. So what was y here? So this was x1 gamma t minus, and now you immediately see why we took the component as well along x1, because so this is gamma t, then in a product with the gradient. So of course everywhere a vector gamma t normalized by the square of the length of the gradient. So normalized by and this is here the gradient. So gradient vector field. Now you simply, of course, there's an inner product outside. Use bilinearity. So the first term simply pops up as I see. Oh, so okay, I'll continue this here. So the first term simply jumps out as gamma t against x1 I mean, gradient against x1 at gamma t. And the second one, you now see why you normalized it the way you did. So that expression there, this one, the normalizing factor, this is a scalar, right? So times the gradient. So you pull the scalar out, the factor of square of the norm gets cancelled. So what remains is the same term as the first term here. So they get cancelled, and therefore you get 0. So this is just the brute force way of seeing this. So this is nonetheless. I said okay. So since so it's not due to any other, a priori orthogonality that we have, because we don't know that y is actually. So what we want to say here is y is in S, right? So that we do not know. So y is a priori only a vector field on W. We want to say that gamma lies in S. So that was the point of the exercise. So we don't know the orthogonality beforehand. So after we know that gamma lies in S, then of course you can go back and say, because on S itself, y is the same as x, and therefore of course this is 0. But at that point in time, you don't know this. So you want to prove this in fact. So, and this becomes 0. Yeah. So that is the sort of the second remark I wanted to make concerning the y there in the calculation. Because at some point I thought, okay, maybe it's it can be a bit misleading. So because you might think, okay, on S they all coincide, but we don't know that gamma actually maps to S. So that was the that's what we are trying to prove. Yeah. So okay. So that those are things concerning what we did yesterday. So I'll still do a couple of results. So I think one I mentioned yesterday, perhaps even stated it in its entirety. So this is concerning reparameterizations of so maximal integral curves merely being reparameterizations. So perhaps first I will show that. So what was the precise statement that we wanted to say? So we wanted to say that, so if we took maximal integral curves, I don't know how I stated this. Let me write it as a lemma or something. So the claim was that, so if we took a maximal integral curve through a point to a vector field, so of a vector field through a point P on your surface, and so suppose your Q is the point you reach on this maximal integral curve through P at time S. Then we claim that the interval on which gamma P is defined, and the interval, so Q is another point, right? So on the curve itself, so gamma Q is another integral curve, now through Q instead of P. So that domain and this domain are related merely by translation, by the time it takes to go from P to Q. And indeed, you only have a reparameterization. So gamma Q of T is gamma P of S plus T. So this is, of course, for every T in IQ. So I perhaps stated it also fully yesterday. Nonetheless, I thought, okay, so we might as well prove this. how does one go about proving this? So at some point we really want to use, so the only thing we have is existence uniqueness. So that's what we will use. So let's define a new curve. So eta variable maybe r to be gamma q at r minus s. Right. So of course the choice of defining eta is really comes from what we want to prove, right? How to relate gamma q and gamma p. That's what we want. So I define eta like this. So you see, we saw so that I gave it as an exercise that translations of integral curves are integral curves. So, right. So since so by an earlier exercise, so translations of integral curves are integral curves. So note here that S is a fixed one, right? So it's just the time which takes to go from P to Q. So we fix a Q here. So R varies while S is fixed. So so if gamma Q is the maximal integral curve through Q, then so the translate is also an integral curve. So eta is an integral curve of X through, so defined where, so wait, so defined on S plus IQ. Why is this the case? So that's the way we define, right? So if if we take a point X in the domain of eta, so this is so if and only if X minus S is in the domain of gamma Q, just the way eta was defined. So this is of course if and only if X is in S plus domain of gamma Q is IQ. So that's why eta is defined on S plus IQ. Now you simply observe. So now notice that eta of S is gamma Q of 0, but gamma Q of 0 is gamma P of S, because gamma P of Q of 0 is Q, right? But Q is gamma P of S. So this is Q. So what we therefore have is eta and gamma q coincide somewhere. I mean, so eta and gamma p coincide at the point S, right? So, and what do we know about integral curves which coincide at a point? They patch together to give a bigger one, right? So on the intersection of the domains, they coincide. Yeah. So the point to notice here is eta and so that is, so let me say, so previous result. So this implies that eta is the same as gamma p on the intersection of their domains, which is what? So eta is S plus IQ, S plus IQ, and gamma p is IP. So you can take these together now. So this implies that eta and gamma p together, are combined to give an integral curve, give an integral curve on the union of these. So this is S plus IQ union IP. So we notice this. So you simply define the new curve to be the restriction. So on S plus IQ it is eta, on IP it is gamma p, and because on the intersection they coincide, it's well defined. So now, of course, you use maximality, right? So far, we haven't used that this gamma p is the maximal integral curve. So now, since IP is maximal, so this forces that S plus IQ is actually contained in IP. So we, of course, want to say that S plus IQ is equal to IP, but so far we've got one containment here. So in order to get the other one, notice that so this implies that for T in IQ, what do we have? Gamma P, let's see, of S plus T. That's what we want to say. So this is eta of S plus T. But this is, by the definition of eta, gamma Q at T. So that's also what we wanted to show, right? So the difference between gamma P and gamma Q is merely the time it takes to go from P to Q, that is S. So, so perhaps I will indicate what we used here. So this is the, yeah, so, okay, so but I just noted that, so I'll leave it like that. So the first equality we just observed, right? So on the intersection of the domains, gamma p and eta coincide. So now, of course, use maximality of IQ. Now, IQ is maximal. So that was our notation, right? So gamma q IQ. And so IQ contains minus S plus IP. So showing that IP is actually equal to S plus IQ. So the maximality of the integral curves is crucial here. Right? So we use that in a central way. Okay, so the proof itself is, of course, simple, but the point to really observe is for maximal integral curves, if you move along the curve and look at the maximal integral curve at that point, compare it to the original maximal integral curve along which you're moving, then these two differ only by the reparameterization, and that reparameterization is given by a translation by the time that it takes to go from P to Q. So, okay. Not a dissimilar proof in some ways. So this is, so the next result is somewhat similar in spirit to what we've seen, and it is as follows. So there's a corollary, because this is all corollary of the theorem. So we have surface, so it's an n surface in Rn plus 1 given by as the level set, so S equal to F inverse of C. So F is something, some function, smooth function from some open subset of Rn plus 1. and the gradient is non-vanishing, so the gradient vector field at at every point on the surface. So the usual, and we start with a smooth vector field on, so C infinity vector field on the open set U. What do we assume in addition? So such that if you look at this vector field, so of course S is contained in U, right, by the very definition. So we will restrict this vector field to S. This is tangent to S. So meaning at every point, yeah, on S, X, every point P on S, XP belongs to TP of S. So that's what this means. Okay, so these are all the hypotheses. Now, what is it that we want to say? So if you start with an integral curve for X and observe that at some point it lies on the surface, then the whole curve has to lie on the surface. Right? So this is, of course, very similar in spirit to the result that we saw. Of course, you can try proving it in the same way and see why that may not work. So, but in spirit, it is very similar to the argument in saying that if two integral curves coincide at a point, then they actually, uh, you know, are the same. So, defined on the same interval. Um, so it is very similar in spirit to that. So, what is the claim? So, if you take an integral curve to this vector field, actually there's no S here, so let me is an integral curve to X. After all, X is defined on all of U. Such that at some point it hits S, then the whole curve has to lie on S. So the proof, of course, is just a little bit of knowledge about integral curves, along with real analysis from your first analysis courses. Okay, so what is it that we have to show? We are given that at some point T naught, gamma T naught lies on the surface. We want to show that for every T, gamma actually lies on the surface. So the whole curve lies on the surface. Suppose not. So we prove by contradiction. So what does suppose not mean? It means that for some T, gamma T is not on the surface. So all the hypotheses of the corollary hold, but suppose the conclusion is not true, meaning that is if gamma T is not in S for some T in I, so we split this into two cases, but so this is just a tool for convenience. So you look at, because we are given anyway that at T naught, it lies on the curve. So suppose this point where it does not lie on the curve is greater than T naught. Then, so the set of points in I, set of T in I, such that T is greater than T naught and gamma T does not lie on the surface is non-empty, and it is bounded below, of course, by T naught. So you can look at the infimum. So then let T1 be the, okay, maybe I'll write it as greatest lower bound. It's helpful to write it down like that because we will use the definition of what it means for something to be the greatest lower bound. So of the set, so the set is gamma t is not in S. So this is non-empty by our assumption and bounded below by the very nature, right? So everything is greater than T naught. So therefore there is a greatest lower bound. Now notice that, so then so notice that f of gamma t is actually C for everything between T and T naught and T1. Right, so this is by the very choice of T naught and T1, right? So T naught is on the curve, yeah, on the surface. So it's certainly it is there, but T0 is the lowest, sort of the least, since it's the infimum here. So everything less than that, it lies on the surface, yeah. But what happens actually at T1 itself, and that, so just by continuity of f and gamma, so limit, let's say t going to T1. So we're interested in what happens at T1 itself, f of gamma t. So by continuity, of course, this is f of gamma T1. On the other hand, when you approach, so it's constant, right? For every t in T naught to T1, this is actually C. So this is C. So continuity argument tells us that gamma T1 is actually also in S. So the greatest lower bound that we started out with, this actually lies on the curve itself. Okay. So far, so good. Now we can use the pretty much all that we know, right? So what do we have to now show? We want to show that. So the way we will do this is the following. Okay, so maybe I'll say this when we actually need this. So okay, so how should it go? Now suppose I take some other, okay, I suppose. So let eta be an integral curve through gamma T1 to, of course, to x through gamma T1 of x. You may very well restrict this to S because we know gamma T1 is in S. That is with so through that point. Yeah. So eta 0 is gamma T1. Now, of course, on the other hand, you have that mere translate of gamma itself also satisfies this. But then, so is gamma tilde defined by gamma tilde of t is gamma of t plus T1. Right? So this is also an integral curve through gamma T1, which is integral to x when you restrict it to S. So now you can use uniqueness. So by the uniqueness of integral curves through gamma t1, so eta equal to gamma tilde on the intersection of their domains. So what does this mean? This means that so mm, so gamma t is gamma tilde t minus t1, which is of course eta of t minus t1, but this is in S for every t such that t minus t1 is in the common domain. Right? And the claim is that we are done. Why? So I claim that this contradicts the fact that gamma t cannot be in S for t very close to t1. So for t, so the question is, why is this true? Of course, if we see that this is true, then we are done, right? Because it says for every t, such that t minus t1 is in the intersection of the domains, you have that gamma t is in S. So you can take t to be arbitrarily close to t1 here. So, but why cannot this happen? So this is where we simply look at the definition of t1. So I'll write that argument in brackets. So the answer to why is, so what was t1? So this was the greatest lower bound of the set of elements in I such that which were greater than t naught and such that gamma t did not lie on the surface. Okay, but what does it mean that something is GLB? So it's the greatest lower bound. So anything bigger is not a lower bound. So given epsilon positive, you simply write out the definition. Yeah? So is not a lower bound. What does it mean for something not to be a lower bound? It means that there is something in the set. After all, what is a lower bound? Right? So every element of the set is actually greater than equal to this element. Yeah? So it's not a lower bound means there is something less than this within the set. So implies that there exists an S in the set. I should have given the set a name because otherwise I have to keep writing the whole set again. So let me do it one last time. And gamma t not in S such that S is less than t1 plus epsilon. So what does that mean? So this is what we claim, right? So which means that there exists an S in I such that S is greater than t1, t0, and gamma S does not lie on the surface with S minus T1 less than epsilon, right? So epsilon was arbitrary here, right? So S is arbitrarily close to T1, sorry, T1 here. So points arbitrarily close to T1, there are always points which don't lie on the surface. But our assumption showed that for every T such that T minus T1 is in the intersection of the domains, gamma T has to lie in S. So that contradicts the argument here in the brackets. And the contradiction arose because we assumed that there is a point greater than t0 where the curve did not lie on the surface. So therefore, every t greater than t naught, gamma for every t greater than t naught, gamma of t has to lie on the surface. So the upshot of this is for every t greater than t naught, of course t I, yeah. So gamma of t lies in S. So that's the crucial argument. Now, of course, the same argument if t is less than t naught. Yeah, so that is just an exercise. So write out the argument. That the analogous argument, perhaps analogous argument for t less than t naught. So this was just to say, so knowing what an infimum is very well is very helpful. So, okay, so all these reparameterizations, etc. I said already. So perhaps, okay, since in the examples that I gave, maybe I write an example here. Uh, I can phrase this as an exercise, I suppose. So in the examples of integral curves of vector fields that we saw, all of them were defined on all of R, right? So the maximal integral curves were defined on the entire real line. But of course, this need not be the case. So I'll give you an example. So your exercise will be to see what's the domain of the maximal integral curve. So in particular, if it is defined on all of R. So what should be the vector field? So consider, let me see. So the vector field X on R. So defined by, so at X is X squared. Calculate the maximal integral curve. Of the vector field through an arbitrary point y in R. So the related question is it defined on all of R? Okay, so what else? I think vector fields, tangent vector fields, etc. Just thinking if I forgot something. That would be okay. So probably not. If I remember, I will write it when I remember. Um, okay, so let's then go to the related notion. Because we are in the situation of hypersurfaces, it's a very special situation. So codimension one submanifold. So uh, we can talk about normal vector fields. So that's what we will do. And towards this, so we'll just briefly recall something topological about path connectedness. So a surface is path connected. So this you know, of course. So for every pair of points on the surface, there is a continuous curve joining the two. So path connected, that is. So okay, is path connected. Let me write out the definition. If for each, so this is something you all know, but no harm in repeating. So for each pair of points, P and Q, there is a continuous curve joining them, which lies entirely on the surface. That's the critical point. So if for each pair of points P and Q on the surface, there is a curve lying entirely on the surface which joins them, continuous curve. So there is a continuous curve joining P and Q. So joining here meaning gamma A is P, that is with gamma of A is P and gamma of B is Q. So from topology, you know that path connectedness is stronger than connectedness. So recall that path connected implies connected. Okay, so example. So this is an example which you can actually write out reasonably explicitly. So the spheres Sn sitting inside Rn plus 1. Here f of course is the norm squared. So this is path connected. If and only if n is at least 1. So n is 0 means there are just 2 points. So S0 is just 2 points, and so that is not path connected. So I'm just wondering if these people had maybe a picture. So it's a very helpful picture in your text. Or the connectedness of spheres. Of course, it's something that you path connectedness of spheres, something that you have to show, but you can explicitly write down paths. Yeah. So given points and spheres. Okay. So it's just an example from topology. Um, so we will assume always that our surfaces are path connected. So that our surfaces. Path connected. Of course, in all these very nice settings, path connected, they are equivalent. In general, they are not. Yeah, so one doesn't have to necessarily make a distinction in this case between whether something is path connected or connected. But I think given that we are dealing with integral curves, etc., I think path connected is a natural way to look at this. Why can we do this? Because otherwise we can simply study the components separately. If it's not path connected, you take all the components of path connectedness and study one at a time. Yeah, that's it. So that's why it's enough to. So it's an interesting. So simply because, yeah. So if not, we can study this. We can study the path connected components separately. So there is actually a nice exercise in the text, which I will mention here. This also is relevant to the comment I made. Why it suffices to look at path connected surfaces. So given any n surface, and any point on it, so you look at the set of all points of S which are connected to P, right? So consider the set of all points where of S which are connected to. By connected to here, I mean the general connected, or maybe joined. Connected to, maybe there's confusion. So which are joined to P by a continuous curve lying entirely in S. So this set itself is an n surface. Okay, so that is one observation to have in mind. So, okay, so we wanted to say about normal vectors, I suppose. So let's go. I think there's enough to. So we needed the notion of path connectedness. So once we have that, so we then have the theorem. So what is the theorem? So you take path path connected hypersurface, n surface in Rn plus 1. So what is S here? So S is a connected, path connected, that is, so is a path connected n surface. Then there are precisely two unit normal vector fields. So unit normal vector fields n1, n2, and they differ merely by a sign. Of course, this should not be surprising at all. So we are in a codimension 1 situation. So the tangent space to the surface, because it's the gradient vector field is non-vanishing, the tangent space is something of dimension n, so codimension 1. So there is one dimension available to the normal vectors, and but only one, right? So if there are two, they have to be linear multiples, scalar multiples of each other. But in this case, they are unit normal vectors, so they only differ by a sign. So nothing about this result should surprise you. So, okay, so let's see. Sorry. So how do I show this? So what do I want to say? Okay, I want to actually, so the way to do this is just define them straight away. So, and there is something normal already, because F is a regular hypersurface. So vector field not zero for every p. Now we can simply define n by normalizing. We want a unit normal field. We know that the gradient vector field is normal. It's orthogonal to a tangent space. There is only one dimension there. So we simply normalize this to give our first vector field. So define by merely normalizing the gradient vector field. So this is the gradient vector field of f p. So this is for every p in S. And well, I have to normalize, of course, by the so we want a unit normal vector field. So the other one is also, you simply define that to be because n1 is already defined for you. So you can define n2 using that. Now what do we have to show? We have to show that these are the only two, because the content of the theorem is there are exactly two unit normal vector fields. So we already have two. We want to show that these are the only ones possible. So it remains to show. So it remains to show that these are the only such vector fields on the surface. So again, this is how do you see this? Suppose there was another such vector field. On S. Then what should happen? Then there's only one dimension available, right? So it has to be a scalar multiple of n1. Why? Because they lie in this one dimensional, since both, there is not too much room. Both lie, so this co-dimension one situation, lie in the one dimensional subspace, which is the ortho complement of in TP Rn plus 1, but that is just Rn plus 1. So when you say, of course, orthogonal to something, then we have to say where. So, okay, so for each p, we get a scalar. So as you vary over points, you get a function. So this implies that there is some smooth function on S. Um, such that n3p is gp times n1p. Again, for every. So of course we say there is and so on, but you can explicitly write it down for all p in S. So okay. So okay, so let me write with points. So this is simply the inner product so you can actually write it out like this explicitly. Now these are both unit vectors, so G has to be plus minus 1. Now, of course, G is smooth. So, so this is for every P. And here's where we lose S is connected. Yeah. So now, so notice that G is smooth and S is connected, meaning path connected. It is constant. As a simply continuous image of a connected set is connected. Yeah. So that's all there is to it. So we are done. Yeah. So N3 is N1 or so this is N1. Oh, sorry, N2. I already put N1. So this is what we wanted to show. So this is why we had to assume connectedness. Yeah? So otherwise, on each connected component, things could take whatever value, right? So then you won't have this sort of uniqueness statement.